Hi all. In this video, we're going to look at what is known as the center of mass. Okay. Now, till now, we've looked at kinematics. We've looked at the equations of kinematics. We've looked at the laws, the three laws of motion, right? And whenever we looked at this, we always talked about a body of mass m. And remember, we always consider this body of mass m as a particle. What do you mean by particle? That is, we said the body had a mass m, but it was just, when we say it is a particle, it means that the mass is concentrated at a point m, right? And this body has no size, right? So when we say a particle, it means the mass of the body is concentrated at one point, and the body has no size, right? So using this, we applied Newton's laws or kinematics. All what we've studied till now, we've always talked about particles, a body of mass m. But let's just look at real life, isn't it? In real life, when we take this marker, for example, it is not a point particle. It's not a particle, isn't it? It has a mass which is spread out. Or let's say I take a hammer. It is not a particle, is it? It is a system of particles. So all in real life, we are actually dealing with system of particles, right? So the question comes: does Newton's law apply to these system of particles? How do you make it apply? Do the kinematic equations apply to these particles? Does the linear momentum apply to these system of particles? Right? So that's something. So that's what we're going to look in this chapter. And when let's say I throw this marker upward, it's a pretty complex process, isn't it? This marker goes up, it goes spinning, and it comes down straight into my hand. How do you analyze this motion? Now, it looks pretty complex, but nature has provided you an incredibly elegant way of analyzing this motion. I call it incredible, right? Because when you throw this marker up, there is a point in this marker where it moves such that all the mass of the marker is at that one point, is concentrated at that one point. I'll repeat this again. That point is called the center of mass. The center of mass is that point which moves such that, in a way such that all the mass of the body is concentrated at that point. Let's say this marker, I throw it straight up and it comes down and I catch it, right? As it goes up, you can see the marker circles and, whatever it does and comes down straight. There is one point in this marker which goes straight up and comes straight down, just like a particle goes up and down. This point is called the center of mass. It moves as though all the mass in the body were concentrated at that point, and it moves as though all the external force you apply on a body. When I put the force on this body, it moves as though all the external force is applied only to that point. So when we analyze the motion of a system of particles in physics, we just analyze the center of mass. That gives a very good idea of what the system of particles is doing. So the laws of Newton, linear momentum, you apply it to the center of mass, and you are able to study the motion of a complex body, a system of particles. Okay. So the first question which comes is, where is the center of mass, right? And I'll just give you an idea to get a feel of where it is in a marker. If I'm able to balance the marker, on my finger, I almost balanced it. You'll see that balancing point, isn't it? Above that lies the center of mass. Similarly, by symmetry, I can hold it like so that right in the middle of it would be that point which is called the center of mass. Okay. Now, but let's try to look at it mathematically. Let's say I have two bodies. Okay. I'm using a coordinate system, and I have a body m1 and I have a body m2. This is at a distance x1. The first body, and the second body, let's say, is a distance x2 from the origin. In such a case, we would say the position, the x coordinate of the center of mass, you find it by m1x1 plus m2x2 divided by m1 plus this would give you the position of the center of mass on the x coordinate, right? So let's say there were bodies on the, there are more than one body, here, and similarly it goes on. So let's say I had a y coordinate system and I wanted to find that the y coordinate, okay, so I have three bodies. This is M3, or let's take another example here. I extend this idea and I say I have three bodies, let's say M1, M2, M3, right? And I would find the coordinates. Obviously now this is a two-dimensional system, so the x coordinate would be M1 x1 plus M2 x2 plus M3 x3 divided by M2, and there would be a y coordinate, okay, of the center of mass, which would be M1 y1 plus M2 y2 plus M3 y3 by plus M3. Okay, so you can see how the more number of particles you can obviously apply. You can using the coordinate system and using this method, you can find exactly where is that point at the center of mass. Now let's say it's a continuous system of particles. It's like, for example, if I were to look at the marker, for example, it's a continuous system of particles. So the way, obviously, you're going to integrate now, and it would be x dm here by capital M, right? Your x of your is going to be x dm by capital M by the going coordinate, and similarly for the y coordinate, it's going to be a continuous integral to find it out. Okay. So that's with respect to the position of finding the center of mass. Now we come to the important question. How does Newton's second law, F is equal to ma, apply for a system of particles? So the way it's going to apply is going to be F external is equal to m a, or in other words, the external force you apply is equal to the mass of the body into the acceleration of the center of mass. That's it. Okay. So to find, when I go to apply, wherever I'm going to apply force on this marker, the acceleration of the center of mass is going to be the force I apply divided by the mass of the marker. That's it, right? Wherever I apply that force in the system of particles. And the way, so this is, the how it applies, and the way I'm going to prove this. Obviously, you want to prove for on this, and keep in mind that this A of center of mass is the linear acceleration, isn't it? This F is equal to ma. I'm considering a translational motion, and this is a linear acceleration that I'm considering over here. Now, the way I'm going to prove this is the position vector, right, of the center of mass is equal to m1 r1 plus m2 r2 all the way till m rn. Okay, suppose there are this n particles, and the position vector of the center of mass is given the addition of m1 into each of the position vectors of each of the particles, the whole divided by m, which is m1 plus m2 plus up to mn, which I'm going to bring on this side and say capital M. Okay. Now I differentiate this. I get capital M. Once you apply the position weight vector, we know we get the velocity is equal to m1 v1 up to mn vn. Okay. I once again differentiate, and I'm going to get m acceleration of center of mass equal to m1 a1 plus m2 a2 plus all the way up to mn an. Okay. Now the force m1 a1, we know this is the force on the particle m1. This would be the force on the particle m2. okay, the force which creates an acceleration in m2. So we can say this is the force that acts on the particle m1, this is the force that acts on the particle m2, this is the force that acts on n, right? And this is equal to m a. F1 plus F2 plus F up to Fn is actually the sum of all forces. The sum of all forces is F external, right? Because all the internal forces are going to cancel out. Keep in mind, all internal forces are going to cancel out. Therefore, all you have is the external forces is equal to ma, which is Newton's second law. So when you apply Newton's second law to a system of particles, and you want to find out the linear acceleration, F external is equal to ma, or in other words, the acceleration of the center of mass is equal to the external force that you apply divided by your the total mass. Okay, and I'll just to give you an example of what really is happening here, right? Let's just consider a billiard ball, right? A billiard ball starts off with a velocity v and goes and hits another billiard ball, and there's a collision that takes place, and then of course both of them move with a velocity v1. The first one gets v1 and the second one gets v2, right? Now when this is, let's say, is m, you can say both are m, okay? Now what is the velocity of the, using the equation, what was the velocity of, I'll give you the concept first. Since there is no external force applying, when this going with the velocity v, it hits the ball and they both move at v1, v2, the acceleration of the external force is zero. The acceleration of center of mass is zero. That means the center of mass is continuously moving at a constant velocity. Think about that. When this goes at a constant velocity, hits this both one, there's a change of velocities, both change in velocities happen. There is a center of mass, and because the collision is an internal force, it is not an external force. And the acceleration happens only if you apply an external force to the system, right? So there's an internal collision that happens, internal forces happen, and there's a change in velocities of the systems of the particles within the system. But the center of mass is just going to continue throughout this journey as though nothing happened. Okay? Thank you.